All right. So once again, what we were trying to do in this lab, we were trying to find the molar mass. There's an equation out there, and it just comes from Piv Nert. If you multiply both sides by molar mass to get rid of n, you end up, and you rearrange it a little bit, you end up with m over v equals dRt, well, equals RT over P. M over v is density. All right, so we are going to ultimately use this equation to solve for molar mass. So in order to do that, we need to find the density. The density, that's a terrible arrow, but we'll get over it. The density was equal to the mass that you measured divided by the volume you collected. But the volume has to be in liters, okay? And you got like probably 0.23 something liters or 230 something milliliters. All right? So this will give you your density. You with me so far? Okay. Once you have that, then you can plug all this in. R is 0.0821. The temperature is whatever you measured plus 273. And then there was pressure. Now pressure was kind of weird because if you remember, in this flask, that's just as bad. Well, probably not as bad as yesterday. In this flask, we let gas bubble up. Let's say that we filled it to here. In this flask, we had some gas and we had some water vapor. The water vapor pressure has to be subtracted out so that this number is an accurate measurement of just the gas. So to do that, it's what we learned at the start of yesterday. We took the total pressure. Now, the total pressure was the same for everyone. What was that? Go ahead. There's heat in the water itself, and that causes a little bit of it. It's not boiling where all of it's converting to a gas, but a tiny bit of it will. Good questions. So what was the pressure yesterday? Was it like 30.84? 0.94 was after we did this process. 29.84? Okay. And that converted to something torr. 759.9. Okay, that's the total. And then based on this table, right here, I'll go back a second, so don't worry. Based on this table, then we found our temperature and we subtracted out this little part of pressure because this was the pressure that water was adding. So someone I helped yesterday did 35. No, that's the example we did, huh? Whatever. So if it was 35, we would have subtracted 42.2 from the total because that was the pressure due to the water at that temperature. All right, so we ended up with whatever that was, and that was your pressure. That number then had to be divided by 760, and that's where Newman got like his 0.94. Right? Okay. Then we would plug all that crap right there, and we'd be ready to roll. We'd have the density. R is a constant. T was easy. We would have just the pressure of the gas, and then we would do that math. Okay. So take a minute and do that math, and then we'll move on to the next piece. Okay. This process is pretty common. Once you have this 4, now we got around 50, so I'll just go with 50. All right, we'll just say it's 50 grams per 1 mole. So the next step, to take an unknown gas, if you know it's a simple hydrocarbon, which it will be because to do it otherwise it's a lot more difficult. you take the mass and you divide it by 12. The reason you divide it by 12 is because a hydrocarbon consists of hydrogen and carbon. But the most massive piece of that is the carbon, because it's 12, hydrogen's 1. So you take and divide the thing by 12, and what do you get here? 4 point something. All right. 6, no, 0.475. Is that right? Let's call it 0.2. Okay, now, the next thing you would do is you would always round down. So you would say 4. And that would tell you your most likely formula for C of the hydrocarbon is C4. Which means that your formula then, if it's a simple hydrocarbon, we did this just the other day, we said that the number of H's is equal to 2x plus 2 if it's a simple hydrocarbon. All right, so X is the number of C's, so we would say this is C4H10. Now, that is what the answer should be. That is the formula of butane. That is what we were looking for, because lighters are typically made out of butane. But there is a problem, because this is not that close to 50, but we'll work through it. Now, if you got a number under 48, then you got 3 points something. Down and say it's C3H8, and that would be propane. Okay, I would accept both from this lab because they're certainly acceptable. There's a lot of error. Then we're just kind of doing high school chemistry in a high school lab. Okay, so in a 1-minute nutshell wrap-up, this is from an AP test question. Okay, it gave you all the data. Okay, we then converted it into a lab at a conference, and we did it. You used the mass and the volume to find the density. You used the pressure of the day and the vapor pressure to find just the pressure of the gas in ATM. Once you have those, you can solve for the molar mass. Once you have the molar mass, then you do the trick where you divide by 12 to find the number of carbons that its most likely is. And every single one of these, by the way, will have like the words, what is the most likely formula of the hydrocarbon? There is some gray area, all right? Once you have that, then that becomes the number of carbons, and then the hydrogens will be 2x plus 2, that value in your. Okay. Additionally, it's very typical, especially from me, to have you then draw it. If it's a simple hydrocarbon, it means no double bonds and then full saturation of hydrogens. That would be good enough. It might ask, the one in the Christmas break assignment asked how many sigma bonds. It could ask how many pi bonds. It could ask for the hybridization of like one of the carbon atoms. Hybridization, you would just count, well, there's 1, 2, 3, 4 electron domains, so that's the sp3. It could ask the structure of one of the central atoms, so that'd be tetrahedral. There's all sorts of places this problem can take you. Okay, fair enough. Now here's the good news. On this AP test question, let's say you did one part of this right, and you got a whole different formula. If your formula is right from your wrong math, you'll get credit for that. You can still get credit for your structure as long as these two match. You can still get credit for this and technically have been wrong the whole time. Okay? So if you make one mistake early, the AP testers do have hearts. You'll get credit for anything you did wrong math earlier above. Okay. Good enough? All right. There's not a test question exactly like this on the test. But we will review what's on the test before we take it. Okay, the next thing we're going to learn, I think I told someone, I think it was probably Emily, that we didn't learn any new math, and that was a little bit of a lie. Did I tell you that? Was it you? Okay. But this isn't, like, once I teach you PivNert in this chapter, technically there is no more math, because it's all a variant of the PivNert law. Okay, this is called the combined gas law. This one's not that bad. It has a ton of variables, so it looks like a nightmare, but it's really not that bad. The combined gas law is used to find the new temperature, pressure, or volume when you have a gas that undergoes a change in volume, pressure, or temperature. Okay? All right? It takes advantage of the fact that if it's the same gas, then N is the same on both sides. So it's just canceled out. All right? Because it's going to say the PivNert of the gas at the start will be the same as the PivNert at the end. But N and R can be eliminated because they're both constants in this fixed gas. Okay? So a useful tool to solve for changes in a fixed gas is the combined gas law. It says that the changes in a fixed gas, and what a fixed gas means is the number of moles of the gas will stay the same, can be calculated by the following relationship. P1 V1 over T1 is equal to P2 V2 over T2. This equation is given to you on the AP test, so it will be given to you tomorrow or Wednesday, Thursday on your exam as well. And there is a question on this. It's in the multiple choice, and it's intended to only take a minute. So the ones just mean like its initial conditions, and the two just mean its change or final condition. So this is just, it's algebra, but it is a tiny bit, it's not tiny, it's very important that you do your algebra right. Okay, I'm going to write it a slightly different way. P1 V1, and I'm just going to make sure it's like up and down instead of side to side so no one gets confused. T1 equals P2 V2 over T2. Okay, so what you need to do, you'll see an example. A child releases a balloon containing that. Now, we know inside the balloon the amount of gas stays the same, right? The moles. So that's why N is gone. It stays the same throughout, and R stays the same. All right. It has these original conditions. What would be the volume, or V2 is what you're solving for, of the balloon when it rises to an altitude where the temperature is now that. So now, I'm just going to use algebra. I'm going to solve for V2. And as long as you are good at algebra, these questions are easy, but some people struggle. If T2 is on the bottom, it's got to go to the top on the other side, correct? Are we okay with that, algebra? So T2 comes up here, and then that's gone. If P2 is on the top, over on the other side, I need it where? On the bottom. And now my V2 is equal to all that stuff plugged into my awesome calculator. I'll put my equal sign over here. What's my new temperature? Now this should be in Kelvin. So it's 284. All right, what is my P1? 761. You can leave that. You can leave that in Tor. All right. What is my V1? 3.5. All right, my T1 was 8. My P2 is now, no, I may have said the wrong variable, but P2 is the new temperature, which is 685. Plug in. It is in Tor. As long as I leave both of them in Tor, I'll be fine. Anybody have that yet? 3.7? All right, and that'd be liters. Thank you. Now, would it make sense that as the balloon got higher that it expanded? Yeah. There's less pressure pushing on it. There's other, but it makes sense. As it rises, it will expand. Okay. Now, these rarely have drastic changes. So if you did some math and you got like 370 liters, double check your work. These changes are usually small, and like reasonable. Okay. That's the combined gas law. It's really just a 6-variable equation that you got to make sure you keep track of everything. Okay? One more time, it takes advantage of the fact that N, or the amount of moles of that gas that's trapped, stays the same, and R is a constant. So we're just doing PIV-NERT twice, but we're getting rid of N and R. All right, there's one more example. All right, I'll write this again in case you need it. Okay, will you try that one on your own? All right, so we're solving for V2 again. We have T2 up top and P2 on the bottom. And then we just plug things in. What did you end up getting? All right, 3.69 liters. Sounds good to me. Our change was that we cooled it. Does it make sense that it would shrink? Yeah, it makes sense. Okay, these are not intended to be difficult or stress-inducing. The equation. It's on the top on one side, it goes to the bottom of the other. You can solve for it. What's that? Well, these two were, and I guess that's unfortunate. You can solve for any of them. It's just a 6-variable equation where I will always give you 5. Okay? That's the end of the math. Now, we will review it, especially like all day tomorrow and whatever time we have left today. The rest is theory. Now, there's like 3 multiple choice questions between now and the end of what I'm going to talk about today. One of the multiple choices was one of these 2 questions we just did, by the way. So hopefully you worked through those. Okay. Here we go. And this is in the book. You can read it. I'm going to go through it quickly. The kinetic-molecular theory, and typically it's called K-MOT. It's just this idea that it's the theory behind the ideal gas law. This is a model that aids in our understanding of what happens to gas particles as environmental conditions change. Now, you do not really need to take detailed notes on this. All right? It's just these ideas. So the main tenets of K-MOT are that gases consist of large number of molecules that are in continuous random motion. Okay, that was like 5th grade that you learned gases didn't have a lot of stuff. They have low densities, and the particles are always moving. Are we okay with that? Okay, they're very, very spread out. All right, next, the combined volume of all the molecules of the gas is negligible relative to the total volume in which the gas is contained. So what that's saying is if we have a balloon, the actual volume that the molecules of gas occupy, like their literal molecules, is extremely small compared to the total volume of the thing that it's in. so we can ignore it. Okay? So when we talk about the ideal gas law, we ignore the fact that the actual molecule itself has an occupies volume because it's so small comparatively. Okay? Another thing says that attractive and repulsive forces between gas molecules are negligible. That's hard for me to say for some reason. What that means is in a gas, a particle will just travel that way, and if another particle gets close to it, they will have no interaction to each other. They are not attracted. They just keep on doing their own thing like the other thing wasn't even there in the first place. Okay? So in the kinetic molecular theory, we assume particles have no attraction to each other or repulsion. Okay? So they just bounce around like a bunch of marbles. Okay. Next, energy can be transferred between molecules during collisions, but the average kinetic energy of the molecules does not change with time as long as the temperature of the gas remains constant. In physics, we call this an elastic collision, which means energy can be transferred, but it's never lost. So when a gas molecule strikes its container, it will bounce back with the same amount of energy it had in the first place. If it were to strike another gas molecule, the combined energy before and the combined energy after would be the same. Okay? So we're saying there's no loss of energy, which means that the only energy, the way that it's changed, is through changing the temperature. Temperature determines the energy of the gas and pretty much nothing else. Okay? Next. All right? And this is what I just said. This is just saying it in a lot more confusing way. The average kinetic energy of the molecules is proportional to the absolute temperature. And that slide and all that is fantastic, but who really cares? The hotter the gas, the more energy it has. The colder the gas, the less energy it has. We okay so far? All right. Now, this has a question at the bottom. So this is more likely a slide that would be important for you to make sure you understand. So here we go. Effusion is a term that you now need to know. Effusion and diffusion. You've heard of diffusion. You've maybe not heard of effusion. Effusion is the reason, like when you were a kid, you got that balloon for your birthday and 3 days later it didn't float anymore. You're like, what the crap? So you trimmed up the string. And then you trimmed it more, and eventually it never worked, right? You're like, what happened to my balloon? Well, it turns out that gases will escape through small holes of the container. And a helium, like a rubber balloon, the rubber is actually porous, and over time, the gas effuses. So effusion is the escape of gas molecules through a tiny hole into an evacuated space. The easiest analogy to effusion is when you guys the bell rings and 300 people are trying to get through that door right out here, right? Whoever designed the building, they must have laughed when they thought, we're going to put a single person door right at the top of the stairs, right at the end of a hall, and all of a sudden every person in the entire school is going to have to occupy the same space. Like, that's the most asinine construction I've ever seen in my life. But if you'll think about it, this is all you at the top of the stairs, and there's the doorway. All right? It takes long to get through that doorway, doesn't it? I wish we didn't have. Imagine if there was no door there. It'd just be free flow. You can't take it out for fire purposes. Those are fire doors. No, I'm with you, but it's never going to happen. But that kind of makes sense, right? All right, now, the important part for you, for your test and for the AP test, is to remember that small things effuse faster. All right? So, possibly, so your helium balloon, that will effuse because helium is the second smallest gas there is. Right? So the rubber of the balloon, you would never think really has holes in it, but it does. Helium effuses faster than air, so that's why it goes flat. All right. So the mass is the number one important reason. The complexity is fine, but the mass of the substance. So talk about this with your lab. So this question is sort of a little bit tricky. It's easy to eliminate 3 of them, right? The bottom 3 are gone. Are we okay with that? Greatest rate means the fastest. So those 3 are big, but these 2 are really similar in size, right? NH3 is 17, CH4 is 16, correct? This is a question. I've changed it on the actual test. This is the old version because I got sick of arguing. But the one that's actually the fastest is A. And I know I just told Boyd that mass is the most important. Their mass is very close to the same, so A is less complex. Okay? On the test, you have this question. Greatest or least, but there's no 2 that are really close to each other, so it should be more obvious. Diffusion is when gases spread out to fill their containers. All right, and the same rules. Smaller and less complex molecules have a faster rate of diffusion than larger, more complex molecules as well. Okay, now there's not a test question on that, but effusion and diffusion, they are different things, but the same rules govern their behavior. Okay, next, real gases. Now, when you go to college and you take any chemistry past this level, which is typically 1210 and you're 1220, this is what this goes to, you will probably have to deal with real gases. And those just straight up suck. There's just no way around it. This is, I'll show you, this is what PivNert turns into when you have to do real gases. But we don't do real gases. So we will talk about them, but we don't do the math, okay? So let's come back. So in the real world, the behavior of gases only conform to the ideal gas equation at relatively high temperature and now that is bold, and parts of it are underlined for a reason. You definitely need to know when real gases deviate from ideal gases. And they are under, well, this is when it tells you they do conform. So when they don't would be the opposite of this, which I think is the next slide. So, an ideal gas assumes all those things we just barely said. It says that, hey, they don't occupy space. They say they don't attract to each other. Basically, it's saying that an ideal gas behaves super different than a liquid would. But sometimes gases will behave pretty close to liquids. And that would happen at low temperatures and high pressure. And what I mean by a liquid, and we'll learn this more in chapter 11 and 13, but a liquid sticks together because it is attractive. The actual particles have some attractive force to each other. In ideal gas, we say there's none. A liquid, the volume of the actual molecules is an important part. Like, it's the definition of the volume of the liquid. It's very different. Okay? So this graph, which might look a little bit weird, it's just saying here is where they behave exactly like we would expect. But as we add pressure, they get very, very different from behaving like a real gas should, or an ideal gas should. It should follow this dashed line, but they all take off and go bonk. Okay? So, an ideal gas and real gas are equal at high temperature and low pressure. That's the number one way to make sure they are not behaving close to the way liquids behave. I think the next slide says this again, but just in case. Okay. The assumptions made in the kinetic-molecular model break down at high pressure and or low temperature. Okay? If you think about this, the more and more I squeeze these molecules together, the closer they become to a liquid. Because a liquid is just when molecules are really close to each other, right? They can still move, but they're real close. And if I keep continuing to pressurize this even more, eventually they become a solid. And we know liquids and solids do not behave like gases, correct? So any condition that would make the gas become closer to a liquid state is where we deviate from an ideal gas. Yeah. Pretty crazy, huh? All right. So, are we okay with when it is ideal and when it deviates? Okay, they break down at high pressure and or low temperature. The pressure, that makes sense, but low temperature should make sense too. All right, low temperature is slowing molecules down. Speaking of slowing, my slate is not going with my hand anymore. So if you have now two particles that used to be flying by each other so fast that they never interacted, but now they're going so slow, when they get close to each other, they actually will attract to each other with what's called a van der Waals force. All right. So hopefully you're okay with that. I don't think I did. There is an ideal gas will deviate from a real gas under the following conditions. There's like two of them, in fact. Okay? So you need to know it deviates pressure, low temperature, same at high temperature and low pressure. Okay, so the ideal gas equation can be adjusted to take these deviations from ideal behavior into account. Don't write this. The corrected ideal gas equation is known as the van der Waals equation, and it looks like that. P plus N2A over V2 times V minus NB equals nRT. And it's not as bad as that looks, because it has to tell you what A and B are. It just takes a lot more typing in your calculator. You are not held responsible for van der Waals equations at all in AP Chemistry, but there they are. Okay, now, technically, I should put a slide in here that says the end. That's the end of Chapter 10. No, the test is in 2 days. So the reason it's in 2 days is so we can have a full tomorrow. Well, we got 7 minutes to work on practice problems. Now, I'm going to practice with you. There's only two free response questions. One's I don't know. To me, the other one's easy. But on Thursday, when we take the test, and you're like, why did we review that problem? Because it's still something you should be able to do, even if it's not on a test. So I believe this question was on your winter assignment, your Christmas assignment. So we'll come back to do this one, but let's look back here at these problems. These problems are typically what I do before we do the lab we did yesterday. So this is a vapor pressure problem. With only 7 minutes left, we can do this. So this is a gas that was collected over water. It says it right here that it's collected over water. That's your gigantic red flag that you have to account for the vapor pressure of water. Okay? So says 193 milliliters of O2 was collected over water on a day when the atmospheric pressure was that. The temperature of the water was 23 degrees Celsius. How many grams of oxygen were collected? Will you try that problem? I'll give you 3 minutes, and then I'll do it in 2 after that. So I already went ahead and rearranged this for the variable I need to solve for, right? If we're going to get grams and do a Pivner, then it must be related to N. All right, since this is collected over water, I have to take my 762, and I have to subtract the vapor pressure of water at those degrees Celsius. So at 23, I look over, and it's 21.07. So what? That's fine. Thank you. All right, 740.93. And now I'm just ready to go. N equals that number divided by 760, by the way. So that's just the P. I'm just putting it in fraction form. The volume, it said, was 193, which is really 0.193, because it has to be in liters. That is over R, 0.0821. That's times T, which was 293. No, 296, right? And then, does anyone have that number handy? All right, 0.0077. All right, and then we just need to multiply that by 32, and we end up getting point what? 0.25 grams of oxygen. How do we feel about that? Yeah, Liam? 32, that's the molar mass of O2. Oops, that's a 2. 32 grams per 1 mole of O2. So to go from moles to grams, you just multiply it by its molar mass. Okay, please.